And here we go.
There's the deluge. Here's ignition.
Roger, roll, Atlantis. Throttling up.
Did it just do a Kerbal?
Back to the moon and beyond.
Put that in the big bag, Jingle.
Back at home, we all have a lot of work to do, but from here, it sure looks like a perfect world.
Propulsion continues to be normal.
We did have an observation.
Equinox.
343 unfolds to go.
It's orange.
Water towers can fly!
Bingo! Right in the center. Where's Jacqueline? There it is!
That was surreal.
That's not what we want to see.
No!
Oh my God.
Yikes. You bet. Sure. We don't need any more of these.
All right, folks, you know the drill. We are live with another Intrepid Museum Astro Live today because we're doing what we do. We get some people who are super smart, scientists, engineers, that sort of stuff from all sorts of different places, and we bring them onto the live show to talk about the cool projects they're working on. We've got two different projects that we're talking about today, but the overarching theme is asteroid defense. What happens if there is an asteroid or something hurtling at the Earth? Is there anything that we can do to change it? Can we make it deflect? Can we make it miss? Can we do anything? Can we send it to the ocean? Do we have any capabilities? There's a lot of science fiction that talks about this. There's a little bit of science fact because some of the folks we're talking to today have done some actual work on studying the asteroids, redirecting an asteroid. Can we do anything at all to deflect an asteroid and change its trajectory in any way, shape, or form? The answer, yes, spoilers, is yes, we did. And we're doing a follow-up mission as well to see a little bit more about how that mission happened. But today, we're going to be talking about DART and Hera, the two missions to the... I'm going to let somebody else say them. Dimorphos and Didymos? I think I got them right. I'm pretty sure I got those right. Y'all can correct me in chat if I didn't. The good news is we have the scientists here who will get it right. But some housekeeping first. It's Intrepid Museum Astro Live. We do these just about once a month in partnership with Intrepid Museum. This is a STEM outreach show, right? We do rocket launch coverage. We do all sorts of different things. But today we're talking with scientists and engineers, so we're going to be focusing on them. If you've got questions for them, you can ask your questions. Tag us in chat at NSF or at NASA Spaceflight. If you're on any of the other channels, Facebook, YouTube, X, wherever you're watching, you can ask questions there. I'll try to get questions from all over, but I can't get them all. But feel free to ask questions. Also, please keep your questions topical. Make sure that what you're asking is sort of the topic that we're talking about right now. If you have a question totally out of left field that doesn't have anything to do with the topic, maybe that's a thing. But also, hey, keep in mind, these shows don't just happen. They happen because y'all keep showing up. You think that it's interesting. We get so many good comments over the show and after the show and that sort of stuff. And then also a little bit of money involved, right? This show is made possible with Astro Live, supported through a NASA cooperative agreement awarded to the New York Space Grant Consortium. So thanks for that. Again, it doesn't just happen out of the blue. It is a lot of work to make it happen. But let's get some folks in here, starting with, from the Intrepid Museum, Elisa Siegel. Elisa, do we have you on today?
Yes, hello. Can you hear me? There we go.
I
Hey,
hear Alicia.
guys. I know. It's so great to be back with you. So great to see you again, Dust, because we missed you last month. But yeah, this is a really exciting topic for us. I feel like for most of our history, asteroid impacts have just been something that happened to Earth. The dinosaurs never saw it coming. And there's been so many amazing movies like Armageddon and Deep Impact and Don't Look Up and all that stuff recently. But for the first time ever now, we are actually entering this era where humanity may actually have the ability to do something about it. We're not just sitting ducks anymore. And again, this was a really exciting topic for us to revisit because some of you out there may have recalled back in 2022, of course, NASA made history with the DART mission, intentionally crashing it into the asteroid moon Dimorphos and changing its orbit effectively around the larger asteroid. But we had to also live stream it. So we were here with Andy Chang, who was the principal scientist on it. And it was so much fun. But I realized we never actually followed up on that. We never actually talked about what happened here. So as you mentioned, we've got some wonderful scientists with us. And not only DART, that was just the beginning. Now, ESA, the European Space Agency, has their Hera mission. It's going back to that system to learn more about the aftermath. So we have a double header, I would say, for you now. We're going to be talking about DART. We're going to be talking about Hera, which it's going to, in the next couple of months, be reaching the system. So yeah, I'm excited. Let's get started.
Also featured in today's show, Elise's earrings. Always topical earrings. They're flashing the camera. They're like glinting on the camera. We may have to ask the scientists to characterize what exactly we have on the earrings there. It looks like they're re-entering right now or something.
They are. They're about to knock my head off my body, but it's all good.
Well, let's hop in the show. Let's meet the scientist that we'll be talking to today. We've got from the DART team, Dr. Nancy Chabot, who is the DART coordination lead. Nancy, how are you doing?
Oh, I'm doing great and super happy to be here today and following up because, there's a lot that happened after we impacted, which was amazing. It was a fabulous smashing success, as we like to say, for that impact event. But so much has happened since then. So super happy to be here today and sort of talk about that.
Excellent. And from the Hera project, we have Dr. Michelle Coopers joining us from Europe right now. It's getting pretty late where you are, isn't it?
Yeah, good evening. It's around 9 p.m. here. Thanks for having me. And yes, we like also to talk a little bit about Hera, who is going to find out what happened in detail when DART crashed into the asteroid.
Outstanding. So it's sort of a 1-2 punch. We had DART that has already impacted the asteroid, and we'll talk a lot about that. We have videos, we have telescope views, we have all sorts of stuff. And then we're sending a follow-up mission. It's already launched, it's on the way, and it'll be inspecting, I guess, another flyby, another satellite that's flying through the area to get more information, which is the Hera mission. Hera? Does it matter which way I say it? How do you say it?
Okay. I say Hera.
Hera. All right, I'll try to say it correctly. I grew up in South Texas. I have a little bit of a farm accent sometimes, so if I say it incorrectly, we all know what the mission's about.
Okay.
So let's hop into this, and let's start at the beginning with DART. We sent DART out to this asteroid system. I can call it an asteroid system, right? Because it's not just one asteroid.
That's what we call it. You can call it a binary asteroid system or double asteroid system, hence the name of the mission, right? DART, Double Asteroid Redirection Test.
It's like such value. Like you don't just get one asteroid in the test. There are 2 asteroids involved. But why double? Why did you need 2? Why didn't you just send it to an asteroid that was like 1 asteroid?
This was really a really clever part of the mission, actually, because, you wanted to measure how much you deflected this asteroid by crashing a spacecraft into it, right? But if you did that, you'd have to measure how much you deflected it around the sun. By going to this double asteroid system, we deflected one small asteroid around a larger one, and we could measure that much more easily. So that really enabled the mission. And here you're seeing those final moments of DART. It's autonomously navigating onto this small asteroid that's never been seen before at this point. And that asteroid's coming into view for the first time. This is Dimorphos. You're seeing the boulders, you're seeing the surface, you're seeing all this rocky stuff you've never seen before. There's about 6 meters, and then then that's it.
So just so everyone's on the same page, let's see if we can roll this video again. This is a series of still images that came down, right? It was an image every some number of seconds.
Roughly every second. The camera on the spacecraft is using it for the autonomous navigation, also sending it back to Earth in real time. And NASA broadcast it out to the world. More than 1 million people watch. So this is an actual image that's getting taken every second by the DART spacecraft coming back to Earth, sending what it's seeing for the first time while using that information to fire its thrusters to try to hit as close to the center of this asteroid as it can. And it hit within 2 meters of the center of brightness. That's how good that autonomous navigation system performed. So, And that little image there is because it's trying to send it back home, but that was the end of the spacecraft. So that's all you got there. But that's within the last second of the mission, actually, right before it hit the surface.
So intentionally crashed into it, navigating itself. You got it close. You got it in the ballpark, right?
Right.
And then once it was there, it was literally looking at a forward-looking camera that's taking these images of the asteroid and deciding that it should crash into it by keeping it in the middle of frame. And if it starts to drift one way, it fires a thruster to correct it, and it just intentionally smashed right into it. How did it know which was the right one?
Well, originally at 4 hours out, actually, it was headed right towards Didymos. And that's
Okay.
when the autonomous navigation came on, because we couldn't see Dimorphos because it's too small. Didymos is so much bigger, 780 meters versus 150 meters. And so that brightness was all from Didymos. And because Didymos and Dimorphos go around each other every 12 hours, roughly. So when DART showed up 4 hours behind, Dimorphos was literally behind Didymos. So it was impossible to see it in those images. So it's just heading straight towards Didymos, and autonomously I had to take these images and been like, how many asteroids do you see now? I still only see one. Still only see one. And it was only within the last hour that it was confident that it's like, I can see 2 asteroids. I can see this one is the smaller one. I'm going to change my trajectory and aim towards that smaller asteroid and autonomously guide myself based off those images. And so this was sort of a really important test for DART, was this technology, this autonomous navigation to target a small asteroid in space that's never been seen before at high speed in order to do a deflection. You can see how this might be something we might want to be able to do in the future if the need should arise.
Gotcha. It's just so cool. We've never seen any close-up shots of the asteroid before, right? We didn't know exactly what it was going to look like. You knew that one blob, I'll say blob, was going to be larger, and one blob was going to be smaller or hidden, not there, or maybe in front of it, but sort of blending into the background. And then you'd have these images moving, like changing over time as you approach, and you had to train the software. Is train the right word? I hope train's the right word.
Yeah, I think that's a fine word. Yeah, no, you're absolutely right, because asteroids, if we've seen from other spacecraft, can have all sorts of weird shapes, right? And so the training of the software had to be able to succeed regardless of what that shape would look like for that small asteroid that had never been seen before. And so they put a bunch of weird shapes for asteroids into it and everything. As it turns out, Dimorphos is, kind of egg-shaped, so it's kind of like normal looking, but, the shapes they trained on were way crazier than this one turned out to be, sort of like dog bone shaped and other, weird shapes. And, you needed a robust system that's going to work for whatever you might encounter. And this is true for planetary defense as well. There's a saying in planetary defense, if you haven't heard it, it is, you don't pick the asteroid picks you. So there you go. See, you don't get to pick what that asteroid looks like. You don't get to pick these things. You have to be ready for anything that comes our way. And so that's exactly what the software had to do too.
I haven't heard that, but I think we just need to make planetary defense more like of a common topic that people understand. It makes perfect sense. Like, you don't get to pick the asteroid.
I mean, so many of our science missions we pick the target, right? We pick it because, like, for science, we pick it, this is really interesting scientifically, or we pick it because it's pretty easy to get to. So, hey, let's go to that one, right? And in planetary defense, it's not going to be that case. You have to be ready for anything that might happen. So it's kind of turning it on its head a little bit, that there's so much overlap between science of asteroids and planetary defense interests. So they definitely are intermingled.
Gotcha. Alicia, as we're going through this, you were there on the stream with us whenever we watched this live, weren't you?
I was. That's right. As I mentioned before, we got to live stream that happening in real time with Andy Chang. And I remember also his reactions. He was also... It was coming to him just as it was happening. He's like, I don't even know if I can say this live on screen right now. But like, oh, the boulders, like we were expecting it to be so much more flat. This is amazing. And like watching his reactions were just amazing. Is this a good time to show that clip? We did clip that because it was a lot of fun.
I think so, yeah. I was sort of
I want to see Andy's reactions. Yes, please.
Let's see if we can get the clip up.
Straight for the target.
Like we're headed straight
As you can see, it's getting bigger and bigger. We're going to hit that big lobe right there.
Look at that. This is a good shape? Like, this isn't a really skinny shape. This looks like a good target, right?
Yeah.
Looks like a good target. The elongation is as we expected. It's not extreme.
Oh my goodness.
But it's enough that, we're going to have to see how big it is. I don't know. It's in the interesting range where you're going to have very complicated rotational dynamics of this body after DART hits. So not only do we deflect it, but we're going to cause it to tilt. Wow, look at all those boulders.
Okay, we are going to stay with this feed right here, and Andy, just keep telling us what you see. We've only got a couple frames left.
Okay, looks like we are heading into a flat area. I can see where we're going to land. We're going to have big boulders right next to us. That's going to have a huge effect on the impact. Oh my goodness!
Look at this.
Yep, this is it's about it. We're coming very. There we go. All right, DART hit.
Look at that.
That's the last image. Yes. Yes, everyone's cheering. Yay!
Do you have pom poms, Alicia? You're like cheering.
I do, because this is amazing.
I have to say,
Oh, that's
Still got him.
classic.
Still got him.
she still has the pom poms.
I'm gonna bring him out for the Hera mission when we finally get some impact information for you guys too.
It was such a special time to be able to get real-time feedback from somebody who worked directly on the project in the capacity that Andy did, and watch his reactions to these images coming back. Never before been seen. He's like, oh, that's what we expected. That's how we care. Oh, okay, that's a little different. It was just amazing. You don't get that. Sometimes data comes back, and then like, all right, in 9 months there'll be a paper about it, right? In that, I'll say this. I can say this. That tends to sometimes dampen the excitement around big accomplishments like this, and to let the public sort of ride along with that sort of experience. It's like landing on Mars. You've seen the JPL missions where it's landing on Mars and you have mission control, and here NASA had their mission control. Yes, exactly. Their mission control live stream that they had going with the reactions of the team in the background, and then to have Andy on and he's like reacting in real time, trying to make sure he didn't like mischaracterize anything, but it's so exciting. I cannot say thank you enough to letting him come on and be on the show and talk to us about this stuff in real time.
And Nancy,
I love the partial last frame.
I'm kind of curious too. What was your reaction? What was going through your mind and your team's minds during those few minutes? Because of course we saw Andy, but
so much. I mean, so here you see, like, this is the mission operations, center at the Johns Hopkins Applied Physics Lab where I work and Andy works. We, built the mission and operated it and designed it for NASA as part of that there. So people were in the mission operations center, and you saw they had been practicing this, working on this for years to get to that moment. We also had a big party outside, actually, with all sorts of watching the live stream there. And then the NASA broadcast was actually from APL as well. And so that's where I was on the NASA broadcast when we were doing this, and sort of these moments were coming in. And so I think just seeing it and seeing how clear the pictures are and seeing what this asteroid looked like for the first time was really, sometimes you work on things for years and you have a lot of confidence in it, but still there's nothing like it actually happening, right? Like, is this really happening? Is this really moment really here? Is this really, all of everything we've been working for is leading to this? And the answer was yes. And, I think kudos to NASA too, right? Because this was never been done before. This was a lot of risk. This could have totally failed, right? I mean, we were targeting a small asteroid that had never been seen in space at 14,000 miles per hour, autonomously navigating in order to try to make that happen. Being able to share that live when there's this chance that it might fail, is a risk. And I was super happy that NASA and the DART team and everybody was able to lean into it, because what an amazing experience. To your point, like, we do this in the United States on taxpayer dollars. We should be sharing it. We do it for humanity, right? This was a very international mission too. The Italians had a CubeSat on it, Licia Cube, that was also with DART contributing to this. We had telescopes active on this project on all 7 continents and in space at the same time as well. And our team members were from roughly 300 people on the investigation team, representing 29 different countries. And then we've always worked closely with Hera, because we always knew that DART and Hera would be working hand in hand to see what the effects are from there. What you're seeing right here, for example, this is from the telescopes in Africa that looked up at the night sky. So while we're celebrating at APL and Mission Operations Center, Licia Cube, they're working in Italy. In Africa, they were looking up, capturing these telescopic images that shows that moments of DART's impact. Michelle, you wanted to say something. Go ahead, jump in.
Yeah, no, I'm just saying, I remember when I see this image, or when I saw this images in the impact night, I was wondering if Dimorphos has survived the impact. Just because of this huge cloud coming out with, I don't know, a kilometer per second or so. I mean, later on, it turned out these are just a few kilos of sodium and potassium that are scattering light very efficiently, but we didn't know that at the moment. And it really looked scary in that sense. Was the impact too good at the end? It turned out it wasn't. But in the moment, it was a little bit scary.
I do say, I mean, people go, what were you surprised by? And we Nobody predicted how much ejecta and how easily visible it would be, in all of these telescopes. If not, somebody would have written a paper about it, and they did not. So that's how they can't claim they did it after the fact. So I think, the fact that we were able to get that telescopic data straight from those telescopes in Africa out there, and they were sharing that, on social media and around the world with the impact images from DART. And then the next morning, actually, LiqiaCube released their images, which you had one up a second ago that showed what that CubeSat was able to accomplish there. Yeah, here, this is a beautiful image from LiqiaCube, and it's just one, and those little boxes there, just to explain, are adjusting the brightness and contrast by a factor of 2 in each one, so adjusting it 2 out. So you can see the fine detail. If we just use one brightness contrast stretch, you can't really see those fine ejecta streamers. So in this image, DART is coming from the upper left corner, hitting into Dimorphos, and you see this very wide cone of ejecta, but it's not just a cone, it's like individual streamers, and there's heterogeneity. And Andy Chang, just like he said on there, that's because of those boulders. That's because the surface wasn't smooth, it was rough, and that really contributed to what you're seeing. But LiqiaCube, it literally is like the size of a briefcase, operating in deep space, 7 million miles away from the Earth and capturing these images. We were so happy to have that contribution from the Italian Space Agency on this mission.
So I've got some questions that have queued up here, and I'm not going to know who the right person to answer each question is, but y'all just jump in because there are some good technical questions coming through the chat over here. Let's start with this one about Hera. So we've seen this big plume that came off after you crashed into it. Is there now a debris field in a wider area that may make flying Hera past more dangerous?
Okay, so what we have seen in those images went away with large velocity and is long gone. And more generally, everything that's smaller than 10 centimeters or so will, by the time Hera arrives, have been removed by the radiation pressure that comes from the sun. Now, with very special launch direction and velocity leaving after the impact from Dimorphos, from larger stuff like boulders of decimeter or meter size that were also seen, for example, by the Space Telescope.
Right.
According to the model, there are solutions that those could survive. So if some material was released with the right conditions, there may be some stuff still around Didymos.
Like unexpected, or it used to not be in the area, but now y'all created maybe a little bit. The small stuff is going to get sort of cleaned up, I guess, by solar wind. Is that the right way to say it?
Yeah, by the solar radiation, essentially.
Okay.
Yeah.
But there might be some larger stuff that's in a new sort of configuration or orbit around the system or something like that wasn't there before.
Now, I also think that intuitively we tend to exaggerate or to overestimate the danger that comes from a few boulders flying around. Simply from the experience, we operated the Rosetta mission at its target comet around an active comet. And there were some issues, but they were not due to collision with stuff. But this was indeed due to smaller stuff that looked like stars and confused the star trackers. There was never an issue that Rosetta could have collided with something. And for that reason, I'm also not worried for Hera.
Gotcha. It was more like a chaff sort of confusing the sensors as opposed to like a physical impact problem.
There was no concern at the time about collision risk. And I think it's fair to say there was more stuff around the Rosetta comet, target comet 67P at the time than we can expect for Didymos when Hera arrives. So.
Gotcha.
Yeah, and Hera will sneak up on the system too, right? Since Hera is not just flying by, Hera is going to orbit,
that's
right? So you guys will start from far away.
Yeah. Hera is going into let's say pseudo orbit, so it's staying with the asteroids for 7 months.
Excellent.
Yeah, I remember when it first collided, the next few days afterwards, everyone was like, "Oh my gosh, it completely obliterated it. It was just a pile of rubble that was very like casually held together or something." Yeah, and that video from Africa, like it really looks like it just exploded. But the goal was never to destroy the asteroid, right? It was just to change its orbit. So I'm curious, like why did we decide to do that versus try to blow it up? I suppose, just in case that were to come to Earth. And if you could also just remind us to how much you actually moved it, because what you were expecting was one thing, but what actually happened was a lot more.
Yeah, so it definitely is impressive, the ejecta that came off. And actually, we watched it for months after DART's impact. For 9 months, you could still see this tail of material that came off after there. It turns out it's only 1% of the mass of the asteroid, roughly, that we impacted off there. Okay, so it's a lot. It's a lot. I mean, by 1%, it's still 10 million kilograms. So that's a lot.
That's a lot.
I'm not saying it's not nothing, but it's still only 1%. Like the asteroid is still largely there and intact.
Right.
This is a model that you're looking at right now for maybe how the asteroid shape will have been changed by that collision, and what Hera sees for the shape of the asteroid when it sees Dimorphos again will be very interesting. But to your question about like, why did we do, and this is, for example, here, this is nearly 2 months, 53 days post-impact from a telescope in Arizona, the World Discovery Telescope. And you can see this tail of ejecta. It looks like a comet, right? That's because of this material that's been pushed off and the solar radiation pressure, as Michelle was saying. In this image, it's about 70,000 kilometers long, this tail of material that you're seeing through there. And so this persisted for months and months and months. But again, only 1% of the mass of the asteroid, roughly, or so. So the asteroid itself is still mostly intact. It was a small nudge as compared to disruption, blowing it up, if you will. So from a planetary defense point of view, if you wanted to do something because it was a collision course with the Earth, you would probably want to do the least amount that you needed to in order to change its path, right? I mean, that's sort of like, let's do the thing that's easiest first to kind of get it on its way. And that's why DART was chosen, actually, because it's called, technically a kinetic impactor technique, which is just a fancy way to say crashing a spacecraft into an asteroid, right? I mean, but you're not doing a whole lot, right? You're just like crashing something into it. You're going to transfer some momentum and you're going to change that future object's path with time. And the way that this would work for asteroid deflection from a kinetic impactor is you would give it a small nudge, which wouldn't be enough to miss the Earth immediately, but after it would add up to longer and longer distance with time. So you would do it 5, 10, 15, 20 years in advance, this small nudge, and you miss the Earth. Now, if you went with the disruption or blowing it up technique, all of a sudden you've got lots of pieces that are doing whatever they're doing. And now you have to worry about all of those as compared to maybe, blasting 1% of the mass off and just having it nudge it and have it change the Earth. Now you've made your problem potentially much more difficult, much less deterministic, and that's probably not the best approach for planetary defense if you could have just given it a small nudge and let that add up to time and avoid a collision with the Earth. So this is the preferred method. It's good to say here, too, though, that planetary defense consequently needs to have a more well-rounded strategy. It's not just about blowing up asteroids or deflecting asteroids. Like, you can't do anything about the asteroids if you don't know where they are. So the foundation of planetary defense is finding, tracking, detecting, and characterizing the asteroids. So you know where they are, you know where that population is. Once we found an asteroid, we can track its future path for 100 years very reliably, for example. So you give yourself that warning time. So you're not in that last minute Hollywood movie scenario where you don't have any good options. If you don't have any good options, then yeah, maybe you have to look at things like disruption. But we don't want to be in that scenario. We want to be in the world where we find and track these objects, and if we need to do something about them, we can go and just give them a little nudge and move them out of the way. So that's what we were working towards here.
That's a big thing I think a lot of people don't really understand, because we see the movies and it's like, I don't know, recommission a space shuttle and put a drilling rig on it and send a nuke. Like, okay, really? Like, that's not, no.
I got one.
Like, you got one we can use, Alicia? Okay, cool.
No one will notice if it's gone. Don't worry about
it. It's missing a few parts on that one, but it's
It's a couple.
It's like a fixer-upper. It's fine. There's plenty of room for asteroid defense.
Flip my space shuttle.
But the most important thing is to find this stuff way in advance, not days in advance or a month or weeks in advance, but years in advance, because the easiest time to change it is when it's still way out there. And a little nudge sort of compounds over time, and if you do a little nudge soon enough, you can make it miss by a wide margin versus, oh my gosh, it hits next Thursday, we have to make a huge change to it to make it miss, right? I think a lot of people don't understand that because you never see that in the movies. Nobody wants to do a movie that's like,
we want to make the most boring movie ever. That's what we want for planetary defense. Super boring
movie. We need to nudge this 15 years in advance, then we're just going to sit here and everybody in the movie's getting old waiting for the asteroid to get here, and then, yay, it missed. Like, that's not as exciting.
It adds up, though. And I think, Nancy, you were mentioning before that originally your goal was just like 73 seconds or something, and then you ended up knocking it off like 3 whole minutes. It was way more effective than you thought.
Yeah, so actually, Dimorphos goes around Didymos every 11 hours and 55 minutes prior to DART's impact. And afterwards, it goes around, takes 33 minutes less, so 11 hours and 22 minutes. And so it was 33 minutes that we changed that orbital period. This is a little cartoon that'll show you again, that going before Dimorphos goes around Didymos, 11 hours and 55 minutes. The telescopes on Earth had characterized it for decades, measured this extremely precisely. And so what happens then is the DART spacecraft came in, right, and it was 14,000 miles per hour, took those images as it's coming. Lichia Cube was kicked off 15 days in advance, sped by and took those spectacular images of the impact. But DART's impact transferred that momentum and deflected Dimorphos around Didymos ever so slightly and changed it actually by 33 minutes. And so our level 1 requirement was actually 73 seconds. So we definitely, but the autonomous navigation was so good. It was right within 2 meters of the center of brightness. So you were hitting it head on, really transferring that momentum effectively. And then all of that ejecta. That's what's really interesting here is you'd be like, why do you need to do that? So like, can't we just do basic physics and know how much we're going to move the asteroid if we do that? The part we didn't know was the ejecta, right? Like all of that material that we were seeing that you were saying like, oh, look at what Africa saw. Look what we see from all these telescopes. That was like an extra recoil effect, an extra push. And it turns out that ejecta transferred as much momentum as brought in by the spacecraft. So it was like a factor of 2. So it is enhanced by a factor of 2 the amount of deflection we got just from the asteroid helping us by kicking the ejecta off in the other direction and asking us this recoil effect. And that's the sort of thing where doing it on a relevant asteroid out in space was so important to do this test in order to advance planetary defense technology.
How is the asteroid characterized? Is it I'm going to ask using the wrong terms. It doesn't look like a solid object. It looks like a loose pile of gravel that's just sort of sticking together due to gravity or something like that. Is that what y'all expected it to be? Because we see asteroids in the movies and it's like, oh, it's one big rock. It's not a pile of loose gravel. Is that what you expected?
I think we're seeing with a lot of these asteroids that they are what we call rubble piles, which is just, like you said, a collection of rocks that are loosely held together, right? Rocks on rocks on rocks.
Right.
And then when you hit it with the DART spacecraft, or we saw with the OSIRIS-REx sampling or the Hayabusa 2 mission for JAXA, all of these have shown that these asteroids are not just solid hunks of material, but are loosely held together. And when you touch them or interact with them or crash a spacecraft into them, they're pretty weak. And so they give quite easily. You get a lot of ejecta, or you go down and you sample deeper than you thought you were going to. So it's really interesting because this is important for understanding asteroids, for science, understanding the solar system, how these bodies evolve. But it's also obviously really important if this thing's coming towards the Earth and you need to do something about it. Like how strong is it? How is it going to react? What are you dealing with? These are fundamental properties. Are all asteroids rubble pile asteroids? Like when they get big enough, we know that they have a core, some of them, and layers, things when they're hundreds of kilometers. If they're really small, are they still rubble piles? We need to see smaller asteroids and see. Maybe some of them are spinning really fast that we know from the telescopes. If they're spinning really fast, it's hard to imagine how this like loosely held together collection of rocks actually stay together, right?
Yeah.
As compared to spin apart. So there's still a lot that we need to learn about the population before we generalize, like this is what all of these small asteroids are like. They have different compositions. Some of them are metal, right? About 5% of all the meteorites that hit the Earth are iron meteorites made of iron and nickel. That would be a very different thing from a planetary defense point of view. And what does a small metallic object look like? We don't know. We've never seen one. These are all important criteria. But I think going back to Dimorphos here, it does seem like it's a rubble pile. We've done some models, which you've seen a few of there, predicting what this is going to look like. But we are so very, very fortunate that we're going to actually be able to get that answer from Hera. Because so often this would be the end of these space missions.
Right.
You would do that, you would make your models, it would look pretty good, but you wouldn't be able to validate it, you wouldn't be able to test it, you wouldn't be able to see, like, is this really going to tell us about that interior property? But instead, Hera is getting there, and Hera is getting there soon, and I just cannot wait to see what this asteroid looks like.
This is a very interesting question, and I don't know if we even have the answer to it. Is there anything on Hera that might be able to detect some trace element of DART that still remains? Like a sensor that can look at it and be like, oh, there's titanium there. That's what DART was made of, and it shouldn't be there if it's not DART vapor or something like that. Is there any possibility, maybe is the right way to ask it?
You should say a little bit about the instruments that are on Hera.
Out there
Yes,
question,
I mean,
isn't it?
often I couldn't think about how to identify something from that on Didymos, but we will look at we will get some idea of the composition. We have a composition, so we have a spectrometer on the main spacecraft in visible and near infrared light, and we also have a spectrometer, and Hera carries also 2 CubeSats. I see, like Ligia Cube also, that went with dark, 2 satellites that are about the size of my laptop that I have in front of me, a bit thicker, but otherwise about the size of my laptop. And those will orbit independently around the asteroid and investigate it independently. And on one of them also has a radar that will actually look into the interior, and this way confirm if Dimorphos is a rubble pile, which is which will be the confirmation also of one main result for me, at least from that even an asteroid that's only 160 meters in size seems to be held together more by its small gravity, than by the cohesion of the material. So that this material is so extremely weak that even at that size, gravity is dominating.
Mm-hmm.
And this, of course, is both scientifically interesting and also important to know for planetary defense attempts.
So it's not another impact mission. That's important.
No, it's not another impact mission. It's a mission that will orbit the asteroid with 3 spacecraft. And then at least the 2 CubeSats will try to land, one on Dimorphos and the other either on Didymos or Dimorphos.
So they're landing. That's cool. I didn't realize that part of it. So you've got these instruments, these sensors. You're potentially landing on it. Very awesome. What is the delay like to send things back to Earth? How soon will we be able to hear some of these findings?
Yeah, the one-way delay time will be around 10 minutes.
Okay, so that's pretty quick. And it's supposed to hit there, I believe, November around then?
Yeah, so the approach to the asteroid is in October, and the insertion in orbit is 3rd of November.
That's amazing. And so what are you both most looking forward to learning from this? I'm sure, Nancy, you've got many questions.
Yeah.
And you as well, Michelle. So like what are you most looking forward to learning about?
I want to see what it looks like.
Yes, what Dimorphos looks like now.
Yes.
Do you have when you go there, have you been keeping track of which side the impact occurred on? And like when you approach it, you'll know like, okay, well, we should be seeing that side now.
This is a funny question.
You're just going to look at it and be like, yeah, that's got a dent in it.
One thing that shows somehow Andy Cheng's brilliancy, when he saw the asteroid, he said immediately, oh, that will do something to the rotation. It will make it maybe tumbling or change the rotation. And this is indeed what we have evidence for from the ground-based data. And that at the same time exactly makes it difficult. So we do have a prediction for the case that it's still rotating regularly, and that the rotation, that the orbit period didn't change anymore a couple of months after the impact. If this is not the case, we simply don't know, which is something else which is exciting to see when we arrive.
Right. I really wonder.
Your question is so fun. Yeah. Andy Cheng really was. Aren't you impressed he said that, Michelle? Like, it was just like.
I was super impressed when I saw that, yes.
Yeah, exactly. When he was just saying that now there, because that's exactly, people did models for 9 months afterwards. Like Andy Chang knew it immediately, but the models 9 months afterwards, showed it, so we thought prior to DART's impact that Dimorphos was like our moon, where it would be like tidally locked. It would always have the same side of Dimorphos facing Didymos. And so we think that's true. And now we think that is not true. Now the models suggest that it's like tumbling, like Michelle was saying. Like, so it doesn't have one size that just faces Dimorphos is tumbling relative to Didymos, so it doesn't always just have the same side that's facing it. By tumbling, I don't mean some of the models don't seem just like a little bit. They mean like it flips totally upside down. Like, what used to be up is down, and what used to be left is right. It's like, like east is west. It's like it's very chaotic, potentially. We don't know. Though. I mean, it's the telescopes have been working since between DART to Hera's arrival, and they've got some amazing data that are suggesting this has actually happened. But it's a very, very tricky measurement. But when you have a spacecraft there that's looking at the system, that is going to be game changing, and that's what Hera is going to do, right? Like, how much did the shape of Dimorphos change, or is there a crater there? There are actually publications in the literature for both of them have made both of these predictions. Some people have predicted there's going to be a crater. Some people have predicted that the shape is going to actually be changed by 10 or 20% of its axis, like changed in shape there, right? And these will be, Hera will tell the difference. That's important because it's related to how strong is this asteroid? Is it a rubble pile through and through? And then implications for how you would deal with an asteroid in the future if it was that weak. And then is it tumbling? That's something else that there. And then specifically also the mass of Dimorphos. We've had some brilliant observations that have been made recently using occultations where they measured that the whole asteroid system, going back to the double asteroid system now, that its center of mass was changed by DART's impact going around the sun by 10 microns per second. 10 microns per second. That's about a change of 1 meter per day. So I talk about it that way because it's like 10 microns per second is too hard for me to think about. But yeah, about 1 meter per day around the sun. And this suggests that Dimorphos is really not very dense, that it has a huge amount of porosity space. For the geeky people out there, it's like 1.5 grams per cubic centimeter. That's like way less than a normal rock that you would pick up here on Earth, which is closer to like 3. So, wow, that's crazy.
Like pumice or something like that, like a really lightweight, porous sort of setup, right?
Super like that. And then a lot of the rubble pile maybe is not put together very well, right? Like that it's got like the macro void space in there. But Hera, so that's a great observation. But again, took telescopes years of data with these measurements in order to do it and really get to there. Hera is going to get there and measure that mass and really be able to like get this definitive measurement, which will test those telescopic observations and just provide us so much more insight into the results of DART's test, how you would apply it to other asteroids in the future. Yeah, go ahead.
It will tell us how efficient the impact was essentially how I mean, we know the amount of we know how much Dimorphos has been moved, but we need to know its mass to know how efficient the impact was due to the ejectors that coming out in moving the asteroid.
Like right now, it's sort of a good guess, but without knowing the exact mass of the asteroid that you start with, you know how much energy you put into it, or from the velocity of the spacecraft to the mass of the spacecraft. You know that because you built the spacecraft, you sent it, right? But you're just sort of guesstimating exactly how much energy went into that asteroid because you don't know the exact mass. And once Hera measures, maybe both, the exact mass, then you can say, okay, if it's that much mass and we changed it by this much, then it absorbed this much energy, or this much energy affected it. I don't know if absorb is the right term there, right? How does Hera measure that? Is it just like, I use this much fuel to go into this orbit? That means the mass of this object is this?
Probably the best measurement Hera can do there is to measure the motion of Didymos through the presence of Dimorphos. It's a little bit like the Earth and the Moon. The Moon doesn't exactly move around the center of the Earth, but they move around their common center of mass. And in this way, also the Earth wobbles a little bit around. And the same we are going to measure for Didymos. So the wobble is estimated to be of the order of 10 meters or so. And Hera will be able to get this quite accurate to 1% or better. And therefore, with the same accuracy, the mass of Dimorphos.
Gotcha. And
Going
that's
back
going
to the like impact where you're saying, Nancy, that like, okay, one theory was the crater, one theory was that it just changes completely. Is there also a third hypothesis that it went because the rubble is like looser and more loosely bound, like we were talking about, could it maybe redistribute all that rubble and make itself egg-shaped again based on the fact that it's rotating and has the gravitational thing? Like, is that even also another option?
The timescales would be interesting. So, you sort of see in that model movie that's played a few times here that you definitely are getting a huge amount of redistribution of material, even in those models. But whether it has enough time between just a few years from DART to Hera to kind of like reshape, people think that processes like those would probably operate on longer timescales. So I think it's interesting to be like, if we came back, 10,000 or a million years from now, that kind of thing. Like, what would this system look like? Because the orbit and the tumbling and all of these things, right? They would kind of, work themselves out on sort of these like larger timescales that are still short compared to the solar system of 4.5 billion years, but long compared to the time between DART and Hera. So, but how much material from Dimorphos round up on Didymos, can we see any things like that, and how much exchange is there between them? Just a lot of really interesting questions. DART was fabulous, but it came in, it smashed in, LiCube really performed fabulous. It got some images and flew by, but Hera's going to stay. Right? That's the difference, right? Hera is there. It can look at things from different angles. If it sees something interesting, it can get more data on it. It's just a whole totally different way of being able to understand the system and get just like the depth of data that we're going to get from Hera is so much more because it's going to stay in the system. And going back a little bit just to the, can we see DART? Right? Because we got this question a lot before DART. Like, are you going to be able to see DART on the surface? So here's the thing. DART was not going fast enough to vaporize. We know that. It would be pulverized, okay? So it would have been pulverized. We do think it will be quite pulverized into tiny little pieces, some of which might have been ejected off. So the best bet, if you're going to find something on the surface, people say, are the large solar arrays, because the solar arrays are about 8 meters each, and they don't have very much mass in them. And they like hit the boulders first, and so maybe some of them won't get as pulverized, but most likely you're not going to see any remains of DART. I think we'd be really surprised. But if you do, look for the solar arrays. So,
is there anything aboard DART, like a material or something like that you wouldn't expect to naturally occur on the asteroid, that if it was detected in some way with a mass spectrometer or something, you'd be like, hey, well, how'd that get there? Is there anything like that, or is it we don't really know what's on the asteroid in the first place?
Yeah.
Oh, what?
I mean, I have to admit, Hera wasn't really designed with the idea of detecting DART.
Detecting DART?
And the methods I could now think of, that I don't think there's anything on Hera that would be able to detect them.
Okay.
If you see a piece of the shiny, solar arrays like sitting out there,
if there's a piece of shining solar array laying around that we could detect,
then you'll see it. But, I mean, this is the thing. We have a good idea what the composition of these asteroids are because they're the most common type of asteroids material that we have there. The telescopes have gotten great data post-impact and pre-impact for what the compositions are. There's a lot of elemental similarities, but how those elements are put together in the natural asteroid versus the DART spacecraft are very different. So there are definitely compounds and things that you don't have naturally occurring on there, but there's not any signature sort of element. So
Gotcha.
I don't know. And I think it would have to be, sort of the imaging and the morphology and, just something broke off in some weird way and miraculously survived. But again, this is highly, highly unlikely. So I think the answer is
not enough to vaporize. So I shouldn't say DART vapors. It's DART pulver. I don't know what comes from DART.
Tiny little pieces.
DART dust. I don't know.
DART dust. That's what we should go with. DART dust.
DART dust. Okay. There's so many good questions here. I'm trying to pick out questions. We're talking about a lot of them in chat. So y'all know some of the questions that I see asking here, like, is there a concern about a debris cloud? We talked about that a little bit earlier. So if we don't repeat some of the questions here, please make sure you go back to the beginning of the show after we're done, and you can watch the topics we already talked about, because some of these questions I'm not going to answer again because we just talked about them probably right before you got here. But
we should say
here-
that there is no danger from a debris cloud.
Yes.
Right.
People
Yeah.
actually did
You're
that
not worried
math.
about
There
that.
are papers. Well, I mean, people were. And actually, before we did the DART mission, we had to file a lot of papers in order to show that the ejecta would evolve in a way that it would become a danger to the Earth. Post-impact, people actually, and Michelle, you were on this paper, modeled exactly where the ejecta would go. And if there would be a meteor stream that you would see here on Earth. And I'll let you share the results there.
Yeah,
Michelle.
it's actually most likely that one could arrive at Mars than on Earth.
Oh.
But not for a while.
The thing is, you need to arrive at a very high velocity for Earth of above a kilometer per second, and to see a meteor, you need the size of a couple of microns at least, or 10 microns or so, and it's not clear if anything reached this velocity to be sure. So it's possible that meteors will arrive, but it's maybe not that likely because of the high velocity, and definitively there would be nothing of a size that could be considered any danger. Definitively,
right. Makes good sense. This is a question because that's one thing that Hera is going to help us understand. What are y'all's predictions for how the rubble pile shape changed? Right, like there might be a crater that you can see. There's now a dip where there wasn't a dip observed before. I wonder if one end there might be a crater so big that it just looks flat, like it blew a side off of it.
Yes, indeed. And it may be that you don't see a crater, and thus the overall shape of the asteroid has changed.
Mm-hmm. Like the whole thing is.
This is what we are looking forward to see, but it's also important because for planetary defense, it tells us how far away was DART from a more catastrophic event that would start disrupting the asteroid.
Right.
And this is important. One could think about other situations. We're not even talking about nuclear, that even the kinetic impactor may disrupt the object. And for those situations, we are now looking into even more gentler possibilities to deflect an object, like with an ion beam, for example.
That was a question that was coming through. Like, what other ideas are there besides just crashing a high-velocity impactor into it? Like, what other ways could we maybe nudge or tractor or whatever an asteroid around?
Like a Death Star.
This is one of them. Essentially, have a spacecraft with an ion beam and continuously pointing the ion beam at the asteroid and gently pushing it away over time.
Huh.
Yeah, there's sort of two parts. So with DART's impact, when people have done models, they do suggest that potentially, if the strength of the asteroid was on the weaker side, that DART's impact, the same massive spacecraft going at the same speed, might have disrupted an object if it was only 80 meters in size. Yeah. So Dimorphos was 150 meters, but if it had been 80 meters, we might have been in the blowing up situation that you were talking about, called disruption. We might have actually blown it into many different pieces. And, which maybe, again, you would want to do that potentially at some point, but you would want to know that you are doing it and not think you are going to deflect it and then cause a disruption event, right? This would not be ideal. So hence, understanding that is important. Here's the DART spacecraft. I love this picture. It's my favorite one of the DART spacecraft right before it shipped off to get launched. And it really just shows you it's a very human-sized spacecraft. So it's a human-sized spacecraft, built by humans to go deflect an asteroid in space. Yeah. Lichia Cube is there on the side, sort of angled up a little bit. And then the solar arrays are rolled up there. They roll out in space, sort of like aluminum foil in your kitchen, if you will. So, rolling out 8 meters there on the side. But yeah, I mean, there's sort of for asteroids, mitigation techniques, ways that you could prevent it from hitting the Earth. There's the impulsive, so it's sort of like a kinetic or something like that, where you would do something that's instantaneous and depart a lot of momentum energy to it. And then there's ones that are called like slow push, right? And that's sort of what Michelle was saying with like the ion beam or a gravity tractor or something like that, where you would slowly act on the asteroid over many, many years, with the ion beams very slowly, operating on it while you're orbiting it, or a gravity tractor that's like tugging it like a little tugboat with the force of gravity to tug it out of the way. These would require you to orbit the asteroid and act on it for many years consecutively in order to get those to work.
More of like a suggestion than you're not like smacking it out of the way. You're like suggesting to it very slowly that it should slightly change its orbit.
You get firmer and firmer with your suggestions the closer it gets. I'm curious for you both. Obviously when people hear asteroid impact, the first thing I think that they think of are these movies, Armageddon, Deep Impact, right? So first of all, that was Hollywood, right? Hollywood's coming up with these ideas and everything. You all are the experts on this now. If we actually did discover that there was a dangerous asteroid heading directly for us, let's say tomorrow, I don't know, like for some reason we just missed it and it just happened to be coming at us. What do you think would actually happen practically today, given what we do know about DART?
Well, you'd have to get a little more specific on your time frames there, I'd say. I don't know if you have heard about 2024 YR4, right? So in December of 2024, there was a small asteroid, 60 meters in size or so, that was discovered to be on, potentially a path to hit the Earth. And they found this in late 2024. And the telescopes kept watching it. So what happened? It's like, oh, telescopes kept watching, and the possibility that it would hit the Earth in 2032 rose to 1%. And that's when internationally there's this United Nations sanctioned committee, the International Asteroid Warning Network, IWAN, and they put out an international global warning about this object, 2024 YR4. That's the name of the asteroid, because it was just like any other asteroid, but it had risen to a 1% chance. Yeah, there is. They had found in 2024, there had already been more than 3,000 near-Earth asteroids found when they found 2024 YR4. It's just, we find asteroids all the time, right? People are always looking up, looking at the sky. So they found this asteroid and it rose to this 1% threshold. And so this global international warning went out to announce that that got more telescopes to look and be like, okay, let's get some more eyes on this object here. And then they found that it rose to 2%. For 2024 YR4, and it actually got all the way up to 3.1%.
Right.
And then more telescopic data dropped that percentage down to 0, and the collision with the Earth was ruled out for 2032. Now, it still remained on a potential course to hit the moon for a while. And so for a while, the potential that it might hit the moon was growing. Recently, James Webb Space Telescope got some more data on it and ruled out a lunar impact as well. But that's sort of, a real world example of how this would play out, right? Like the first thing is it's not going to be this, oh, it's coming and it's heading tomorrow. It's going to be like this first glint of information from some telescopes with a big uncertainty, right? And then everybody's going to start looking at it more, and that uncertainty is going to get less and less. And this played out over a month in order to get to that point, right? So what if it had stayed on a collision course? There's protocols, at least in the United States, where you would maybe want to try to send a recon spacecraft to go see what you're dealing with and see what you're looking with. And even though this one was found the last minute, the impact was still going to be in 2032 potentially. So you still did have this 8 years of time, which is not necessarily enough for all of your mitigation techniques potentially, right? But enough time to do something about it. So I don't know. It depends on how it's going. We do tabletop exercises here at the Johns Hopkins Applied Physics Lab, and we involve other government agencies, including FEMA. So we do like disaster preparedness strategies, which would be something. If you knew something was coming, you would want to handle disaster preparedness on the ground as well. These have been international tabletop exercises. So it's really a complicated situation depending on what you're looking at. But the more and more steps that we can take with things like DART and Hera and these exercises and future in space opportunities, the better prepared we'll be.
And also, 2024 YR2 would have been a bit of a stress test for the system had it been an impactor in terms of the lead time, with 8 years between detection and the non-impact, but the potential impact. But also now with new surveys like the new Vera Rubin Survey Telescope in Chile and the upcoming NEO Surveyor and NEO Mir missions, who are looking in space into the objects that are difficult to get because they arrive from close to the sun in angle, or from a close angle to the sun. We expect that with those facilities, also those lead times will increase. And if something arrives, will us give a bit more comfortable time margin to do something about the impact.
Gotcha. This was a question that came through chat. Do we think that it's possible that we could send multiple spacecraft, like hit it once and hit it again and hit it again?
Yes.
How long? I guess it depends on the asteroid and its orbit. But how long does it take for us to get a spacecraft from Earth to an asteroid? How long did it take for DART to go from launch to the impact?
There was a 10-month cruise, so it launched in November and then it impacted in September of 2022. So that was 10 months, but it depends on the specific trajectory. You know, it could be less, it could be more, depending on you want to do that. Using multiple kinetic impactors, yeah, that's definitely something people have thought about, and maybe that gets around this disruption problem potentially too, right? Like a few small pushes as compared to one catastrophic one. You kind of want to make sure you time those so they're all hitting in the right direction. You don't want to kind of like nudge it this way and then nudge it that way, right? That's not going to be productive. But if you had a lot of lead time, you could imagine, you know, every time it makes its cycle around the sun, you send another one, see how it did, send another one. You know, if you have years of warning time, you have a lot of options and a lot of opportunities. And people definitely do think about multiple spacecrafts. It's really important to say, like DART, like that T in DART is for test. You know, this was a test. These asteroids were not a threat to the Earth. And this is not the only end all be all of what you would do. It's just so exciting because DART was the start, right? Like it was the first time we did a test in space, and it needs to like not be the last. There's a lot more that we need to do in order to actually be ready for when something is on a collision course with the Earth.
Yep. Not only were they not already a threat to the Earth, but you had a very high degree of confidence that what you were going to do was not going to make them a threat to the Earth. Like, what happens if you hit it and then you put it on a collision course?
You mean like 100% confidence? That's what we mean by 100%. Like, we had a very high 100% confidence level that we were not going to. Yes, there was no chance to make it a threat to the Earth whatsoever. We just knocked, like, Dimorphos now orbits slightly closer to Didymos than it even used to be before. The change around the sun, like we said, was 10 microns per second. So yes, totally safe.
Decreasing its orbit relative to the larger asteroid. It's not even like, oh, we might knock it out of orbit around that asteroid.
It's even more bound than it used to be.
Okay. I think we had a graphic of that showed the orbit of the Earth and the orbit, like the spacecraft going to it. So if we could grab that, I think that'll help people understand sort of where this was. Because that's also, we mentioned when we were looking at these assets, why we got such good imagery of it from the ground. Because when the impact occurred, it was close. What are we looking at here, Nancy?
Yeah, so right now you've got the sun in the middle, and you've got the Earth in its orbit, and then you've got the Didymos asteroid system with that gray line out there. So DART launched off the Earth in November of 2021, and it took 10 months in order to get to the Didymos-Dimorphos asteroid system. But you can see when it did this in fall of 2022, as this plays out, that this was not just any random time that we decided to hit the asteroid. It was so important to take advantage of this 2022 opportunity when the distance between the Earth and the Didymos asteroid system was at a minimum. Actually, this minimum wouldn't be there again for another 50 years. Now, it looks close in this animation, but it's still 7 million miles away, so totally safe. But this allowed the telescopes around the world already existing to get amazing data, highest quality data that they had ever gotten on this asteroid system, and capture those moments like we showed of the impact and the ejecta tail, and to measure how much we deflected it, again, from using those assets that already existed here on the Earth. So this is really a clever test. So it really was like a good way to do this first test of asteroid deflection.
You even had the sun sort of like acting as a backlight, right? The sun was behind the Earth relative to where the asteroid and the impact was happening. So it's not like the sun was blinding you so you couldn't see it. The sun was helping you light up the ejecta and that sort of stuff, right?
It actually helps too with the way we were able to see the shadowed size of Dimorphos from Diddy shine, as we call it. So the sun is hitting the larger asteroid, Didymos, and it's actually reflecting slightly onto that dark side of Dimorphos, if you will. And when we got those images down, and if you stretch them super, super hard because of the Diddy shine, as we call it, we were able to see like more of the full shape of Dimorphos than we would have been able to otherwise. You know, that sort of part that's in shadow there of the actual images. If you stretch them really hard, that Diddy shine is illuminating them. So Diddy shine, not an official scientific term potentially, but it works.
So-called, like, hey, it's a colloquial term. We like it. It'll make people talk about it more. Like, that's important too.
Yes.
So, okay. There are tons of questions that continue to come through. I will just continue to ask questions because we have the right people on to help answer them. Is there any expectation, since this is a rubble pile, is there any expectation that the interior composition of the asteroid might be different than the exterior composition of the asteroid? And will Hera maybe be able to see a difference?
Yeah, maybe not so much in composition, but it could be that the porosity, the makeup, let's say the physical makeup is different in the interior from the outer, very much from the very outer layer. And that's is something we will see with the Juventus CubeSat that will go there with Hera and will operate independently around the asteroids with the radar. This will exactly answer questions like that.
Gotcha. Do you mind if I just keep sort of rapid firing some Hera questions? Because I've got a whole queue of things here. I actually don't know the answer to this. I know launches work this way, but why didn't we set it up so that Hera arrived before the impact and was on station when the impact occurred?
Okay, we didn't really set it up like this. So Hera, or there was a predecessor mission for Hera that was called AIM, that was proposed to the ESA's ministerial conference in 2016 to arrive just before that. And I maybe need to explain here a little bit. In ESA's so-called optional program, where Hera is, the missions essentially need to get sufficient funding from the now 23 ESA member states, essentially to be able to run. And in 2016, the AIM mission did not receive sufficient funding and couldn't go ahead at this time.
Gotcha.
But still, there was considerable interest in some countries, so studies were continued. And those ministerial conferences are every 3 years, so it's a conference N19, the slightly modified mission, also with a new name, Hera, was then approved and got full funding and could go ahead. But by then, it was too late to arrive before that. So we are now arriving 4 years later. But luckily, not much changes on an asteroid within 4 years, so you can still see the outcome of the impact. The one thing we cannot see are the ejecta, because they will be largely be gone, except maybe the few boulders we talked about before. But luckily, we have much information about them from Ligia cubes that flew by just a few minutes after the impact, and also from the Earth and space-based observers. So overall, we are fine also with Hera being there 4 years later than that.
Gotcha. It's a funding thing. I'll say this. I live in the United States. I pay taxes, and there are little check boxes on your taxes sometimes, and it's like, do you want to fund this, that, the other? If there was a checkbox on my taxes that was like, do you want to kick in money for asteroid defense? I would check it. I would be like, yes,
everyone
please.
should
Spend
everyone
some
should
of my
check
tax dollars on asteroid defense. Yes, please do that.
It's important for all of humanity. Everyone should be checking that box.
I would check the box. Chat, would y'all check the box? I mean, I would check the box. I would put some money into asteroid defense. How long do you expect Hera to be operational for when it reaches the system, goes into orbit? What's its planned mission lifetime?
So Hera's nominal mission goes up to June 2027.
Okay.
And we are in the process of proposing an extended mission for Hera.
Good.
That would stay there a little bit more and potentially fly by another asteroid, and or if we see that still things are changing in the dynamics of the system, we may also consider to come back like in 2029, but also things are currently just proposals that still has to be improved again by those who provide the money to us.
Right.
So
it takes money.
The current answer is the end date for Hera is June 27, June next year, but there is a possibility that it may be extended.
Is that a fuel limitation? Like it has X amount of propellant, and so it can stay in orbit
Actually,
for that long?
We are in the lucky situation with Hera that we have plenty of fuel.
Okay.
And the reason for that is you always need a backup for a mission in case something goes wrong.
Right.
And the backup, in case Hera wouldn't have made the 2024 launch, would have been a launch in 2026 with a different trajectory to the asteroid and with a trajectory that would have required much more fuel. And now this difference in fuel between the 2026 and 2024 mission, we have in principle there for anything we would like to do extra, given we get the funding for it.
Right.
And actually, we have already used a little bit for that when Hera flew by Mars in last year. We timed the flyby to get close to Deimos and to investigate the side of Deimos that is opposite to Mars, which so far hadn't really been much investigated in general.
Okay.
Those are actually what we see here now is a video taken from the images from the cameras on Hera during the Mars flyby. The cameras are monochrome, so those images are artificially colored, but otherwise it's the original images from Hera. So we see here still the approach phase. Now around 40,000 kilometers from Mars. And now the phase starts where we see that the observations become brighter, where we look for Deimos.
Right.
First, Deimos in the field of view while we're approaching Deimos with the cameras. And then the trick the mission operations team played is that found it out in terms of spacecraft maneuvering. It's easiest to observe Deimos from nearby when you look at it if it is in front of Mars. And those are the images that we are seeing here.
Oh.
And the closest images of Deimos that we were seeing now were taken from about a distance of 900 kilometers, roughly.
Wow.
And then Hera got still closer to Deimos, but we couldn't see it anymore. And now it's followed by the closest approach by Mars. I should say the prime purpose of the Mars flyby was to get some acceleration to Hera to get it to Didymos. But we have taken advantage to use those Mars images for calibration of the instruments on the spacecraft, and also for some scientific observations from Deimos, which we are where we are submitting the publications now.
Very cool.
And at the end, we also got a glimpse of the other Martian moon of Phobos.
That's so primarily you were doing sort of a can I say Martian slingshot? You were getting a little bit of extra trajectory from Mars.
Maneuver,
yeah. But while you were there, you had all your sensors on board. You had power. Why not use it to take some pictures, check some things out, calibrate some? Nice. And that's really interesting. I hadn't thought about that, where you planned for a later launch date, but if you had taken that later launch date, you would need more fuel to do your trajectory to get to the target.
Yes.
Since you made the earlier launch date, the spacecraft, it's not like you took the fuel out of the spacecraft, right? So you have this extra fuel that you can use to extend the mission if we can keep the lights on the ground, which takes fun.
Exactly.
Right. that would be a major bummer. I'll say major bummer. That's not a technical term. But if the spacecraft is there and it's operating as intended and it's got extra fuel, like, it would be a bummer if we didn't take advantage of that fantastic scientific opportunity and use it to go somewhere. You said it could leave the Dimorphos system. It has enough fuel to sort of like do its orbit. And then leave
because
and go
Didymos and Dimorphos are so small, you don't need much fuel to leave the system.
Gotcha. It's like a little nudge to just leave because their gravity is so low.
The gravity is so low,
Wow. These are the types of things, like, you hear the headline about the Hera mission, you hear the headline about the DART mission, and that's like, okay, cool, and then you move on. And when we have conversations like this, and we learn all of these little details and the things you've thought about and the opportunities that we still have and why it's, like, that's why we do these shows. Thank you so much for coming on and answering all these questions.
I saw something in the chat. Yeah, I saw a question in the chat that I actually wanted to ask about. I thought it was kind of interesting. So, we're using Mars as a gravity assist. Everything has its own gravitational pull, right? The question is, how well does the moon act as a gravity tractor or a shield against asteroids aimed at Earth? So let's say there's like a small, very small, whatever, thing coming towards us. If the moon happened to be kind of hitting towards its area as it's coming in, might it get swung up into the moon instead of like actually impacting with us, or is the moon not strong enough to do something like that?
The moon is, I think, about 80 times less massive than Earth, so it would have to come very close to the moon before hitting Earth to have an effect.
Yeah.
Got it. So it'd have to be very close.
Plus, you run into sort of like both situations. There are situations where the moon could steer it away, and there are situations where the moon could steer it into Earth. Like, you don't get to choose, right? So...
But like, I don't know, just using the moon as a gravity assist the other way. Like, make it go that way.
Make it go that way.
Yeah. That's a good question.
Let's see here. I'm trying to catch things that we haven't already answered before. I'm curious here on the rubble pile. I'm trying to figure out the right way to ask this. Is a rubble pile style asteroid more likely to make a crater, or less likely to, let's say, have a crater form? Is it like you need a certain amount of cohesion between the stuff? So
I would say the rubble pile asteroid is less likely also because much of the energy of the impactor could go into the compression of the target, because the rubble pile is also really porous, and then you get less of a crater than with something more cohesive, where the energy essentially goes into excavating the crater.
Gotcha. I'm thinking about it in terms of like sand, right? If I'm on the beach and I throw a ball down at the beach, it's easier for me to make a dent in the sand than it is if I'm on a granite slab or something, right? I can't dent the granite slab.
But that's a bit you're at a different velocity.
A slightly different velocity. I can't throw a ball like 17,000 anythings per hour. Okay. Let's see. There's a lot of questions about the data that has come from DART already and how that's being used to model how we can affect asteroids. But do we need to hit more different types of asteroids? Do we need, now we know about rubble pile asteroids. What can we actually use the DART data for beyond, yes, confirmed we can change the orbit of an asteroid?
Yeah, I mean, I think it's a good point, right? I mean, so that was DART's, what did we do to Dimorphos was an important part of it, right? Like demonstrating that humanity has this ability to deflect an asteroid in space. Monumentous, right? And we saw the impact, and that was spectacular, right? But really the reason that we've been doing all the modeling and looking at the ejecta and talking about the rubble piles is because it doesn't actually really matter as much what we did to Dimorphos. It's more, what did we learn so that we could apply it to other asteroids in the future? Right? This was really key. And that's why you have to do these things to gain that understanding, to know which are the things that are specific for Dimorphos and which things can be applied to other asteroids in the future. That's why, going back sort of to the planetary defense strategy, if you will, you have to find, track, detect them, and characterize them. When we do these tabletop exercises, or when we do other sort of scenarios playing out, a lot of times what people want to do right away is send a spacecraft to go look at this asteroid. So you would send a recon spacecraft in a potential scenario like that. So this would be an asteroid that maybe just flies by quickly, but it gets you images of what it looks like. You can see what the surface looks like. Does it look like a rubble pile? Does it have a bunch of rocks all over it? Maybe if it's big enough, you can get the mass of it from some technologies that you've been demonstrating out. You can get its overall shape and its size really well, right? So you know what you're dealing with. You'll get some compositional information, right? So you don't have to plan for every potential opportunity space, right? And then divine your mitigation based on your knowledge that you have from that target. And I think the more we're seeing from each of these asteroids and learning about them is that we are learning things, but we're also learning that understanding the target that you're dealing with is really crucial to matching your mitigation approach to it. And hence, planetary defense, one of the priorities that's in the national strategy is to have this rapid recon capability, if you will. If we found something and it was a threat to the Earth, it's sort of like flying a plane into a hurricane, right? What do you want to deal? You've got this threat coming up. Let's go get more information and fly into it and see what we're dealing with. And those data that you get to inform, the threat assessment and everything are crucial when it comes to these other natural hazards. This is a natural hazard in space, and so getting that information quickly in order to inform you, I think then lets you inform which models to use, how to use them, and which mitigation takes to approach. So thinking about it again, where we're just going to sit here and, and wait and send something, an asteroid out to it, I think we can do better than that, right? We can send these resources into space, like we were talking about with Rubin and Neo Surveyor, find, detect, track, have these years of warning time, develop a capability where we can rapidly go and scout out what a potential threat might look like, and have that information, and then use that to inform how you would mitigate it. So I think that's the sort of the answer. But all of these are just not what did we do to Dimorphos, but how would you apply it to other asteroids in the future?
And that's also an important objective for Hera, to really get as much information as possible about Dimorphos to be able to extrapolate the result of that to another asteroid when we need it.
So if there were another large asteroid, larger, let's say, asteroid coming towards us, what would you take away from DART and everything right now? Let's say it's a little bit bigger, would you try to send another DART spacecraft that is just a larger spacecraft, or would you try to ram it faster? Or what do you think could, obviously the recon's important, obviously everything will be different, but all things kind of roughly considered the same, it worked. So would you try to just do it again, maybe on a different scale?
Yeah, I mean, I think if you have the warning time and you have those years, decades of warning time because you found this thing, sure, you could do it with a larger spacecraft at faster speed, or you could use 2 spacecraft, like we were talking about, 3 spacecraft, right? Maybe that's better, right? Because you already have demonstrated DART and you can rely on that heritage and that demonstrated performance and just do something like that multiple times. Maybe that's lower risk than, having to go faster. For example, for your impact speed, right? And be able to have your autonomy have even less time to do the autonomous tracking. These would be scenarios that would get played out. There's no like clear, obvious answer today, but yeah, go ahead.
Sorry. I mean, one aspect about the warning time, as we discussed it a bit before, I mean, in most cases, the time we have is not determined by the time we need it to between launch and getting to the asteroid. In most cases, the overall time is determined by the time you need to build the spacecraft. And there in the future, one could think about the rapid return concept where spacecraft is waiting either on Earth or in space on its target.
Mm-hmm.
And if you allow me 20 seconds commercials, we are now going to try this for a different purpose with a Comet Interceptor mission, which does exactly this and waits in the Lagrange equilibrium point, essentially 1.5 million kilometers behind the sun from the Earth, in this case to be able to encounter a long period comet for the first time. But the same concept would also be applied to planetary defense.
So instead of, oh, here's something interesting coming, we're going to launch now and go for it, it's, hey, we have the spacecraft, we're going to launch now, and we're going to put it sort of on station, like loitering in this Lagrange point, and then when we get a good target that we know that we can catch up to with the resources available on the spacecraft, we're going to send it. But we don't have to worry about waiting for a launch slot or weather or anything like that. The spacecraft will already be ready to go.
Yeah, and that could work for some, but maybe not all. It goes back to the you don't pick the asteroid.
One for all,
You don't pick the asteroid picks you, right? So if you need to be ready for anything that might come, a lot of times you are better just launching in the right direction. But, I think
so for reconnaissance, it could work for a lot of objects.
Yeah. Yeah. And so I think another thing to take from planetary defense is it's not just a one size fits all. We talk about a toolkit a lot of times, right? And at my house, I have more than just a hammer. You know what? Screwdriver is super awesome too, as is the saw sometimes, right? So it's like the same thing for planetary defense. You need to have like a toolkit of options in order to deal with, the wide variety of things that you have out there. I mean, space capabilities, we're seeing more launches every single day, right? And so it's not unreasonable in this day and age to have spacecraft stored in space, have spacecraft stored on Earth, right? This is like, both of them, right? And just sort of, keep your options open.
And not starting from scratch. It's like, oh, we need to build a spacecraft from scratch. This always gets me. It's like satellite buses where it's, we already have everything designed. We just need to put these specific sensors on it and send it, right? Having a design that already sort of works for this or other purposes seems to save so much time. Right. And you always run into, is it the latest, greatest technology versus is something we designed 5 years ago, but it's still fine enough? I mean, if we're crashing into an asteroid, maybe we have pretty good technology right now. We proved that DART could do it. Right. But just having something ready to be thinking about it is the most important thing, not just sitting on our hands and not doing anything until, oh gosh, now it's an emergency, right? That would be the worst thing we could do.
Yeah, well, I really hope that'll be part of the legacy of DART, sort of, doing this first demonstration for planetary defense technology in space. It really should just be the start. The legacy should be that we move from the technology demonstration missions to an operational capability. An operational capability means that we're ready, right? It means that, we've got the spacecraft ready to go. And when we do have that asteroid that's on a cosmic collision with us, we can do something about it.
Yep. We need like a technology readiness. Go ahead.
Well, no, I was just going to say, so like looking ahead, like 20, 30 years, where do you hope planetary defense is? Is it that we have all these things stationed and ready to go to just hit a button when you need it? Or are you going to be investigating other tactics to try to offset things? Or where do you hope our future goes with planetary defense?
I really think, go ahead.
I think the main advantage advance in 20, 30 years could be that by then we know most of the dangerous asteroids, at least, let's say, of the size of Dimorphos or larger.
So we are. We are on track to do that with Rubin and with Neo Surveyor, 140 meters and larger. And then all of a sudden, you really are in the scenario with something that's Dimorphos size and larger. You have decades of warning time, right? I also really do want to think that in 20 or 30 years from now, that we do have some things that I would consider an operational capability for planetary defense. And that means not just building it when we need it or demonstrating something, but that we're, that we really do have spacecraft ready to go to deal with the potential threat that might arise from something on a collision course with the Earth. And so that's ready to go. And at the same time, I do think that you'll still be improving technology, like we were saying. Like sometimes things are good enough, but you can always do better, right? So this should go hand in hand, right? As you're developing the operational capability, you get a few basic things in there, sort of like your recon capability, be on Earth or in space or both. Maybe you've got a few kinetic impactors, sort of like some contracts out there with people who could do things like that. But then maybe you're still working on the ion beam and the gravity, tractor or some of these other ones, and sort of to, just keep improving the toolkit and to, prepare our planet to be ready and be able to not go the way of the dinosaurs.
Yep. We have a slightly better space program than the dinosaurs, so we've got that going for us so far. That we know. I mean, I haven't done any dinosaur spaceports of y'all. Here's a really good question, and we're sort of coming up at the end of our time here. People want to continue following along with both the data that came from DART and reports and papers and stuff like that came from DART and Hera's mission going forward. What's the best place to find data sets and papers and stuff like that? Is there one sort of clearinghouse or website? Let's start with DART that people can check out.
The NASA websites are the best ones. So if you just, and if you haven't done this, for fun fact, if you go into Google and you type like DART mission, there's a little spacecraft that cruises across your screen. It passes and your whole screen tilts, literally. If you haven't done this, you need to do it. You need to do it right now. So I would suggest doing that, actually. And then you'll get the links to NASA DART, and that's a fine way to do it. But, I'm so happy when Google rolled that out. We had no idea that it was happening, but it's a really cool little effect that if you put DART mission and then spacecraft. That said, like DART and Hera have been joined at the hip and involved in this through the whole time. And, DART was the active mission. We ended in 2023. And now it's the time for Hera, right? So really go to Hera, right? That's where you should. All right, there you go. See? Isn't that awesome?
I did not know that.
There you go. Learn something every day. But really, Hera. This is Hera's mission. Hera's time.
Hera,
go to Hera. Yeah.
So for Hera, what's also new for Hera is we will the releases of new images in near real time during the Hera mission will go through the Hera.space artificial intelligence agent. And let's say for the more archival use, let's say as an operational archive during the mission, we have a data hub at Altec, where we can provide, I guess, afterwards the link. And at the end, the data will be archived in the same way as the data for that in the usual planetary archives.
Oh, the Hera.space was the website you said there. I brought it up over here, and it's like a chat, and it's got a log of all the different things that have happened and that sort of stuff. And the data is sort of going into there, and is more updates.
It is being updated, and now you can talk to it and get information about the spacecraft, where it is, and some information about its state right now. But it will be updated to also provide those images that are essentially the subject of the images that will be released essentially directly after arrival on Earth.
Wow, that's actually really cool. We should put the live stream in there. Want to watch a stream about this? Here's a live stream we should recommend you go watch. All right. We did start just a couple minutes late. We were chasing down one small technical bug. It was an orbital calculation problem that we fixed it. It's fine. So we got the stream going, but we are coming up on the end of the show here. So let's do one more thing. We've heard so many different things. I know I haven't been able to ask every single question that came through chat. But Nancy, Michelle, is there anything that we didn't cover here that you really think people should know about asteroid defense or inspection or recon? Michelle, start with you. Is there anything that you wanted to say that I didn't ask you?
Maybe a more general thought is asteroid impact is one of those threats that we really don't think about in our daily life because it's something that happens very rarely and well, it most likely won't happen in our lifetimes. But it's something where we are the first generation that can do something about it, and we should be prepared, even if it's unlikely. And it's something that it's difficult to grasp. I mean, I have been telling this now for several years. But then in 2020, I was completely unprepared for a pandemic or completely unaware that it may be a good idea to have some face mask at home.
Right.
So it's really something which I think is difficult by human nature to really consider seriously if it's something outside the daily experience.
Right. Makes sense. Nancy, how about you? Did we miss anything? Was there something like, gosh, I wish they would have asked me?
No, I mean, I think though one thing that I really do want to emphasize is just the international nature of this effort for planetary defense for what is an international concern. We're all on this planet together and we're all working on this together. We literally on DART had all 7 continents involved and, like I said, 29 different countries, and Hera is the same sort of way. And this is really just the start. We're moving towards this new era where we can protect our planet from cosmic impactors, and it's no longer just science fiction. It's getting to be science fact.
I like it.
Yes.
All right. Well, folks, hey, we do these shows once a month. We're going to talk a little bit about what's coming up next in the next Astronomy, or Astro Live, actually. But in the chat, please let us know what you thought of the show. A huge thanks to Dr. Nancy Chabot, the DART coordination lead, and Dr. Michelle Coopers over here as well, Hera project scientist. Thank y'all so much for taking time out of your weekend to answer our questions and talk about all the cool stuff y'all are working on. It really means a lot to us that y'all came on the show and spent time with us.
Well, thank you very much. This has been a pleasure.
Yeah, thanks to you for inviting us. This was really fun.
Excellent. And chat, do this as well. I'm going to tell you, it is very important. If you thought that this was interesting, you got some value out of it, you think that this sort of stuff needs to be done, put it in chat, because your chat messages get saved, and then when we send this around, other people can watch it, especially the people who approve our guests who come onto the show. We can say, look at how important this is for people, because they said it right there in chat. We'll cut out the part where I prompted you to say that. No. But please, if you think it's valuable, please let us know in the comments down below, because this really is a good time. But again, Nancy, Michelle, thank you so much for spending time with us today and taking time out of your weekend. Now, Alicia, let's talk about the next show that's coming up, shall we?
Sure. Well, yes, once again, thank you both for doing this. Again, this was really cool to revisit years later, now that we know a little bit more about DART and everything. And of course, we'll all be watching the Hera mission as it happens in the next couple of months too, when we start hearing about it. But otherwise, if you all are joining us from the New York City area, first of all, we hope that you've had a chance to come out to one of our World Cup viewing parties. We've had such amazing turnout, throughout the entire time they were playing, and all the support. So thank you for tuning in for those. And also now coming up this week on Friday, we've got our next free movie night up on the flight deck. It'll be July 31st. We are showing a classic for us, National Treasure, which actually shot a scene on Intrepid on the flight deck, exactly where you will be sitting if you join us. How could we not? How amazing. So please come on out and join us for that. Of course, weather pending. And of course, also be sure to tune in to us next month, August 16th, for our next episode of Astro Live. We're going to be speaking with people at NASA's Human Exploration Development and Operations Office, aka HEDO. So this is the team that works on payload integration and operations for things like Artemis. And they're also working on habitation development for the upcoming moon base as well. All over the news these days, we're very excited about returning to the moon, of course. So we are looking forward to speaking with them a little bit about what they do there, and also what's coming up on the moon. So as always, if you're interested in finding out more, you can head on over to intrepidmuseum.org, and we'll have a bit more details on that on the next few days.
All right. And folks, remember, again, at the end of the show, Astro Live supported through the NASA Cooperative Agreement awarded to the New York Space Grants Consortium. Thank you all so much for showing up. I did see some people supporting the Intrepid STEM outreach over there in the chat. We greatly appreciate that. But plus, just showing up in the show, making comments, talking to each other, asking such good questions. Make your family watch. put it up on the TV, send it to your mom or whatever. I'm sure my mom was watching this one today. I'll probably have text on my phone like, ask this, ask this. Then I'm like, oh gosh, I didn't ask mom's question. But please share it with your friends, share it with your family. So many people show up for the big rocket launches and the big things that happen, and SpaceX Starship goes, and then people show up, and so much work goes into missions like this, and more people need to know about it. So please share it with your friends and family. The link that you're watching on right now, you can share around, you can email it, you can text it, you can post it on social, whatever you want to do. But thank you so much for showing up and helping us make these shows possible. Alicia, that's going to be the show for today, and we will see y'all folks next month in the next Intrepid Museum Astro Live. Thank you so much for watching.
Thanks, everyone.
And here we go.
There's the deluge. Here's ignition.
Traveling up.
Did it just do a kerbal?
Back to the moon and beyond.
Put that in the big bag, Gino.
Back at home, we all have a lot of work to do, but from here, this sure looks like a perfect flow.
Propulsion continues to be normal.
We did have an observation.
343 unfolds to go.
It's orange.
Water towers can fly!
Bingo! Right in the center. Where's Jacqueline? There it is!
That was surreal.
That's not what we want to see.
No!
Oh my God.
Yikes. You bet. We don't need any more of these.
Right, Jay? All right. We've got Twitch. We've got Intrepid's Facebook. We've got Intrepid's